Okay, so we've been talking quite a bit about aromaticity. And one of the things about aromaticity is that the electrons in the pi system are much lower in energy than a simple alkene. And so one must overcome this aromatic stabilization energy for a reaction to occur. So we haven't really talked about any reactions yet. But in this particular reaction, the electrophilic aromatic substitution, we react the benzene ring with a really strong electrophile. One that would normally have actually a full positive charge and thus a really low LUMO. Another way of doing this is to add a substituent group that increases the nucleophilicity of the benzene ring, raising the HOMO. But let's do actually the first case, where we take a benzene and we react it with some really electrophilic molecule. We'll call that E+. Okay, so this is a generic electrophile. What happens in this reaction is that you will break aromaticity. So the pi CC will attack the electrophilic ion there, and this will give what's known as a sigma complex or an arenium complex. And so this arenium complex has a positive charge, a new bond to the electrophile E. All right, and so this is called an arenium complex. And we referred to it before as the sigma complex. And this sigma complex or arenium complex has has resonance stabilization, so we can move the positive charge around the ring. And so let's do that. We've got a new positive charge there at that sort of central carbon. We can move it around the ring even further to give us this resonance form. And we said that what happens in this particular case is that instead of having some anion attack that positive charge, what happens is we get a loss of aromaticity, or loss of the proton to reestablish aromaticity. And so we get a loss of this proton, and the driving force is that now we have an aromatic molecule that has substituted a hydrogen for some electrophile E. And the reaction coordinate diagram for this is kind of as follows. So we have the benzene ring at a really low level. This leads us to the arenium complex here, in which we've got the new bond to the electrophile. And then there's some break, and I'm gonna break this to illustrate the point that we're not exactly sure. It kind of depends on the electrophile which one of those two steps is rate determining. Sometimes the rate determining step is actually the deprotonation. Sometimes it's the formation of the rhenium complex. And so we kind of draw this the reaction coordinate diagram like this to indicate that we're not sure which one it is. Okay, so this is the generic mechanism for the electrophilic aromatic substitution reaction. And so the arrows that you're going to push here are going to be exactly the same, but the only difference is that you're going to change what the E+ is, what the electrophile is. And so what kinds of electrophiles are used here? Well, let's go through a couple of those. Right, the first reaction we're going to come across, one in which we've discussed already, is the halogenation reaction. And so the halogenation uses some halogen, X+. All right. Notice that it's not something like X delta plus. Right. That one doesn't work. All right. So Br2 is not strong enough. And this is remarkable because bromine is actually a really reactive molecule. Right. So X+ needs to form, and so in order to do that, we must add a Lewis acid. Okay, so we've got a Lewis acid. So let's say we take bromine, and we're going to react it with the Lewis acid iron tribromide. What we get here is a complex known as an 8 complex. in which we've got a bromide plus and an iron tetra bromide with an anionic charge on the iron. Right, so this is known as an 8 complex. Okay. We can also take bromine in the presence of aluminum tribromide. That also gives us the same 8 complex, but this time we've got an aluminum with a negative charge. And this can also happen with chlorine by taking aluminum trichloride to give us the chloride plus aluminum tetrachloride minus. Okay, and so now each of these molecules will react with benzene. Let's just take these first two, because if they react with benzene, according to that same mechanism that we just drew on the previous slide, we're going to end up with the same product, bromobenzene. Obviously, if we took the chlorine with aluminum trichloride, react it with benzene, we're not going to get the bromobenzene, but we're instead going to get the chlorobenzene. Okay, and the key point here is that the mechanism follows the generic one. The only difference is that you form this 8 complex at the beginning. How does this 8 complex form? Well, the Lewis acid will tug on the bromine, or in this case the chlorine. It will tug on it, and so what ends up happening is the electrons kind of move over and form a positive charge on the halide, negative charge on the metal center. Okay? And so what happens is that reacts now with the benzene ring, forms your sigma complex. You can perform resonance delocalization, and finally loss of a proton to give you reestablishment of aromaticity. That gives you the electrophilic aromatic substitution product, in this case bromobenzene or chlorobenzene. All right, let's do another one. Let's do nitration. Okay, so what's the E plus in this case? The E plus in this case is the nitronium ion, NO2 plus. Right, so normally here we use a combination of nitric acid and sulfuric acid. But there are stable salts that are rarely used, and I'll just show 2 of them here. The tetrafluoroborate salt and the hexafluorophosphate salt of the nitronium ion. All right, each of those is a source of the nitronium ion. And so let's actually draw how you would actually form this nitronium ion in the first place. So we can draw the Lewis structure of nitric acid as follows. So nitric acid has this Lewis structure. If we're in nitric acid in the presence of sulfuric acid, we have a proton source. So let's draw in the protonation event that would occur. We're going to protonate that oxygen atom of the nitric acid, and that's going to give us this intermediate here, in which we've got kind of a protonated nitric acid, so positive charge on oxygen. And this is a really unstable species, right? Very unstable. And you can kind of see in this molecule, it's got actually a good leaving group. It's got this water molecule in here. And so what can happen is you can get the lone pairs on oxygen to kind of come in, form a pi bond, and then water will leave. And so what ends up happening is you'll generate the nitronium ion. So nitronium ion is this one here. And this nitronium ion will, again, via that generic mechanism, react with benzene to give you nitrobenzene. Okay, so generic mechanism here. This time what will happen is the benzene will attack the nitrogen atom. Of course, you got to break something, and so you generate the negatively charged oxygen atom. Undergo your resonance delocalization, followed by deprotonation to reestablish aromaticity and give you your nitrobenzene. Okay, so that's the second electrophile. Let's do a couple more. All right, the next one is known as a sulfonylation. Okay, so in a sulfonylation, the electrophile is SO3H plus. All right, this is the sulfonium ion. In this case, we're going to use sulfuric acid in the presence of SO3, sulfur trioxide. This is often referred to as fuming sulfuric acid. And as the name describes, it is indeed fuming. All right, so what happens here is we have sulfur trioxide, and sulfur trioxide in the presence of sulfuric acid will become protonated. And so we can take the oxygen, protonate it to give us the sulfonium ion as such. And so this is the sulfonium ion. Here's our E+. This will then react with benzene via the generic mechanism. And so the arrows will be pushed like this in the first step of that generic mechanism. To give you your sigma complex, resonance delocalization, followed by deprotonation to reestablish aromaticity, and then your product will look like this, which is known as a sulfonic acid. Okay. Okay. Let's do another one. The next one actually has a name. It is known as the Friedel Crafts acylation. And in a Friedel Crafts acylation, we're going to be using what's known as an acylium ion as our electrophile. And now this can happen in two different ways. So let's do the first way. The first way is in an intermolecular process. So this is between two molecules. Okay, in intermolecular processes, we use a Lewis acid and either an acid chloride or an anhydride. Okay, so let's do the first case. Right? So the first case in intermolecular processes is use of a Lewis acid and an acid chloride. So in the case of an acid chloride looks like this. It's got some R group, a carbonyl, and then a chlorine atom. All right, so this is an acid chloride. And you might imagine that if you took this acid chloride in the presence of a Lewis acid, what will start to happen is that the chloride will be tugged on by the aluminum. And so you have a sort of a transition state here in which you've got now the chloride is making a bond, starting to make a bond to the aluminum. And actually, it can be helped by those oxygen lone pairs. And so what can happen here is the oxygen lone pairs can come down, form now a triple bond, and then this carbon-chlorine bond breaks and makes a new bond to the aluminum. And so what you end up with is this species here, where you've got a positive charge on oxygen, plus the aluminum tetrachloride. And then that thing reacts, of course, with benzene via the generic mechanism. And so the carbon atom attacks the carbon of the acylium ion, breaks that carbon oxygen triple bond, right, forms that sigma complex intermediate, does the resonance delocalization, followed by deprotonation to give us, as a product, this ketone. Okay, so now we have a carbonyl that has been attached to that, that benzene ring. Now, how does this work in the case of an anhydride? Well, it works actually fairly similarly. So what's an anhydride? An anhydride looks like this. So this is an anhydride, sometimes known as an acid anhydride. And we can react this with some Lewis acid. Let's react it with aluminum trichloride again. We can also react it with something like zinc chloride. It's just a Lewis acid. And what we're going to get is, again, a transition state in which we're basically tugging on the aluminum trichloride. And so these lone pairs here can come down, form a new triple bond. These electrons can move over, form a double bond, and that electron, those electrons can form a new bond to the aluminum. And so this gives us, again, a acylium ion. This time that acylium ion is has a spectator or counter ion that looks like this. We've got a negative charge on that aluminum. And this, of course, can react with benzene once again via the generic mechanism. We've got the benzene ring attacks the carbon, releases the triple bond up onto oxygen as a set of lone pairs. They form that sigma complex, resonance delocalization, followed by reestablishment of aromaticity after you lose a proton to give you your ketone. All right, so these are ketone functional groups. Okay. One example of this, and you can draw this mechanism at home, is to take a benzene and react it, let's say, with this anhydride here. Now, this happens to be a cyclic anhydride, and in the presence of aluminum trichloride, what will happen is you will get a new carbon bond to a benzene ring, and then the rest of your tail is the rest of that anhydride functional group. Okay, so this is the only first case of FriedelCrafts acylation. These were the intermolecular processes. What happens if you have an intramolecular process? Well, let's do that case. So this is now B, intramolecular processes. Intramolecular processes use protic acid or a Lewis acid. Okay, so the example here is, let's take a carboxylic acid we're going to react it with, let's say, phosphoric acid, H3PO4. So if we draw phosphoric here, we could have also used sulfuric acid or methane sulfonic acid, which we abbreviate like this. I'll show you the structure of that in a second. Toluene sulfonic acid looks a lot like tosyl chloride. Triflic acid. Really, it's just a proton source. Well, what happens here is you get the oxygen lone pairs on the carboxylic acid become protonated. This gives you an intermediate that looks like this. Very highly unstable carboxylic acid. But what can happen is those oxygen lone pairs can come down and kick out your water molecule, and that's going to give you the acylium ion. Once again, that acylium ion can, of course, react with the benzene ring. This is going to be an intramolecular reaction, so I'm not really drawing that out, but this is an intramolecular step. You're going to follow the generic mechanism. You form a carbon-carbon bond, and you get product. So what does this look like in terms of an intramolecular reaction? Well, let's actually just kind of take a molecule that's very similar to the one we just drew. And so if we had this benzene ring and it has a tail like this, and we react this carboxylic acid with methane sulfonic acid. And so methane sulfonic acid looks like this. And so methane sulfonic acid can protonate that carbonyl, or that carboxylic acid, proceed through formation of the acylium ion, and then get attacked by the aromatic ring intramolecularly to give you the sigma complex, perform resonance delocalization, followed by loss of a proton to reestablish aromaticity, and what you'll end up with as a product here is another ring. And so the other ring will, of course, have that now new carbon-carbon bond in between the benzene ring and the carbonyl. This particular molecule is known as alpha tetralone, and it has a lot of importance in organic chemistry for the synthesis of larger molecules. Okay, so those are a couple of different ways to add some electrophile to a benzene ring. Now, so far, if we had to describe the types of groups that we do the ring, we are adding groups that we say are deactivating. Okay, what does it mean to be deactivating groups? Deactivating groups are all electron withdrawing groups. Right? So these would pull electron density from the pi system. Right? So pull electron density from the benzene ring. All right, and this is going to lower the HOMO, and of course lower the LUMO as well. Right, so adding a deactivating group onto the benzene ring will make it actually less reactive. Right? So if it's lowering the HOMO, it's going to be less nucleophilic, right, once added. Okay, so what is the how could we rank the substituents in terms of their ability to deactivate? So which one of these molecules is the most deactivating? So right, okay, let's take a benzene ring. Let's add some electrophile E plus, and let's put it on there. Now, once it is on there, which substituents are going to be the most deactivating, so that it won't react even further. Right, it turns out that it follows the trend as I indicate here. So the nitro is actually the most deactivating, followed by the sulfonic acid, followed by the carbonyl, followed by bromine, chlorine, and then, of course, hydrogen. Right? So this one here, the nitro group, is the most electron withdrawing. Right? So the most deactivating. Okay? And of course, what that means is that the one that has hydrogen is the least deactivating. And of course, that makes sense because the one that's hydrogen is just benzene itself. Right? So least deactivating, this is closest in reactivity to benzene. Okay, so we've added deactivating groups onto the benzene ring. You know, what if we didn't want to add a deactivating group? What if we wanted to add an activating group or an electron donating group to the benzene ring? Well, we can actually do that. And that's the fifth reaction that we're going to come across, which is a little bit different, but it still reacts via that E+. It's only now we're going to add it, we're going to add an activating group onto the ring. Okay, so the fifth reaction here is known as the Friedel Crafts, and be careful of the name, a Friedel Crafts alkylation. And so this is different than the acylation. This is a Friedel Crafts alkylation. And the E+ here is really just a carbocation. It's a secondary or primary carbocation. All right, so how could we generate a secondary or primary carbocation? Well, we use our tried and true method, which is to take some sort of halide and react it with a Lewis acid. And so we can do that here by, let's say, just taking tert-butyl chloride, reacting it with aluminum trichloride, and that's going to set up a transition state in which we've got this tert-butyl chloride is being tugged on by the aluminum trichloride. And what ends up happening is that the bond breaks, and we can get a carbocation. This happens to be tert-butyl cation plus aluminum tetrachloride. And then that, of course, reacts with the benzene ring, right, via a Friedel Crafts alkylation. You attack the benzene ring with the pi cc, attacking that atomic p orbital. You generate the sigma complex. That sigma complex then does the resonance delocalization, right, followed by loss of a proton to reestablish aromaticity. And now you've got a new carbon-carbon bond to form. Now this reaction is actually very difficult to stop at the monosubstitution because the initial product is actually more nucleophilic than the starting material. Now this wasn't the case in when we added deactivating groups onto the benzene ring. The product of our reactions were less nucleophilic than the starting material, so we didn't have a problem. But now we have a system in which we've got electron donating groups onto the ring, and so this HOMO is actually higher. And so what happens is this reaction occurs again. And so it's very difficult to stop this reaction at the monosubstitution. And so your product mixture will be something like this. And so you've got you're going to get a mixture of these di-substituted products. Okay. Now, one pitfall to this reaction is that some carbocations are subject to rearrangement. And so we can see that in the case of this example. So if we have a benzene ring, and we're going to react this benzene ring with, let's say, N-butyl chloride in the presence of aluminum trichloride. Well, we know that primary carbocations don't like to form, but how could we explain that we get this product mixture? And so we get a 35 to 65 mixture of those two isomers. Well, how does this occur? Well, the major pathway proceeds through a rearrangement to a secondary carbocation. So let's see how we generate that E+. All right, so we've got this chloride here. We're going to react it with aluminum trichloride. That's going to set up a transition state that looks like this. So I'm going to say here I've got a bond to chloride. I'm going to rotate around that bond a little bit to give me this here. So what I'm doing here is I'm rotating around that bond. I'm putting that alpha group towards the back, and then I'm making a sort of semi-bond to the aluminum trichloride. So it's, again, tugging on that system. And when it tugs on that system and finally breaks that bond, all right, what can happen is the hydrogen can actually move over. So the hydrogen's moving over at the same time that the carbon-chlorine bond is breaking, and what you end up with after that set of arrows is a secondary carbocation plus aluminum tetrachloride. And again, that can undergo reaction with benzene via the generic mechanism, right, to give you the uranium complex, resonance delocalization, followed by loss of a proton to reestablish aromaticity, and lo and behold, we can get our product that looks like it's been rearranged. All right, now the second case here, so the first case was using an alkyl halide plus aluminum trichloride. The second case was actually, we can use an alcohol plus a protic acid. Right, so let's actually do an example of this. So let's say we've got a benzene ring, and this benzene ring has the following alcohol at the end, and we're going to react this alcohol with, let's say, sulfuric acid. So I'm just going to draw out sulfuric acid. We can get this alcohol to become protonated. We know this from first semester chemistry. The alcohols are easily protonated to give you protonated alcohols. And protonated alcohols have really good leaving groups on them. And so the leaving group can leave, this time it's water, and that generates a carbocation, of course. And this carbocation can then react with our benzene ring in an intramolecular sense, again by attack of the pi system onto the carbocation to generate an uranium complex. Right, this uranium complex undergoes resonance delocalization followed by loss of a proton to reestablish aromaticity, and then you now have a new carbon-carbon bond has been formed. Right, so this again operates by this generic mechanism. Okay, so we've got some other groups that we can add to our reactivity series. We said that if we wanted to rank these molecules in terms of their ability to deactivate benzene systems, we said that nitro was all the way on the left. Right, nitro is the most deactivating. Then we've got sulfuric acid, sulfonic acid, excuse me. Then we've got the carbonyls. Then we've got bromine. Then we've got chlorine. Then we've got hydrogen. And on the opposite side of hydrogen are now the R groups. And so we can kind of group these into, okay, we've got benzene in the center here. There's our non-deactivated and non-activated system, or so that's the center of this system. And what we have on the left-hand side are all of the deactivators. And of course, on the right-hand side, we've got the sul activator so far. Right, so those are all the alkyl groups. And what we're going to do next time is actually extend this, this reactivity series to many, many more types of functional groups and see what effect that they will have on the overall reactivity of the molecules.